Now we want to do a simple projectile motion. This problem is almost identical to the one we did in lab. In this case, what we want to do is find the range, how far this thing will go on our picture here. We'll put that range down right there. And we're starting from this hilltop. Hilltop is a height h. That h is given to us by 25 meters. The initial velocity is 300 meters per second at an angle of 25 degrees. So the very first thing we want to do is complete our picture as much as possible. We put as much information on there as we can. We can use g as 9.8 meters per second squared, and we can put a coordinate system on there. And I guess I'll make my coordinate system blue. And I'll put my coordinate system right there where the ball is fired. One of the other things we want to do here is break that initial velocity into the components in that coordinate system. So that's going to be v0 in the x direction and also in the y direction. So now I like to write down the equations that we believe we'll be using. So in this case, we'll have the x direction, and we'll have x as time of flight equals x0 plus v0 in the x direction times time plus 1/2 acceleration in the x direction times squared. And in the y direction, we'll have same thing. Y is a function of t equals initial position, velocity, and time. We also have the velocity equation. And that may or may not be useful to us. So given this x and y direction, I literally think of this as a table where I'm working in the x direction and working in the y direction. I'm going to now list all the things that I know. Things I know. X after a time of flight, well, that's r. Now I don't know r, but that's the range I'm looking for, so I'll just write it down that way. x0 equals 0 because I've chosen my coordinate system to be right at the origin of where the ball starts. The time of flight I don't know, but I do know acceleration in the x direction. I know that's 0. Over on the y side here, I know that y after time of flight, well, that's equal to a minus h. Since I chose the coordinate system on the ball, it will fall down below the height of that cliff. So that'll be some negative number. V0 y, that's going to be that V0 sine 25 degrees, where my 25 degrees is right there. Now, my time of flight, again, I don't know. A sub y I do know. That's that minus 9.8 meter per second squared. I now put the minus sign on there because I see it's down in the opposite direction of my chosen y direction. And I think that's about. So I'm going to roll the page up a little bit, give ourselves some working room. These are things that I've written down that I know, but I'm going to continue on with my table format and start plugging in. So in this x direction, I'm going to have r equals v0 cosine 25 degrees. I forgot that I put that there, but I will now. Times time. And there's nothing in the a direction. I'm going to call that number 1. And I'm going to highlight those two variables I don't know. So there's an equation with two unknowns in it, and I only have one equation so far, so I know I'll need at least one more equation. Over here in the y direction, I fill in the things I know, So I'll have minus h equals v naught sine 25 degrees times time minus 1/2 g. I'll just use the symbol g instead of the 9.8 just since it's easier. T squared. Now I could go ahead and solve for t, because this here is another equation where, again, I don't know that time. Is there anything else I don't know? No, it was not. Well, it was given. I guess the h is 25 meters, the v is 300 meters per second, so I know all those values. T is the only thing I don't know. So I can go one of two ways. I could either solve for t out of this number 2 equation, or I could solve for t out of the number 1 equation. I don't know what's better. I guess I'll go ahead and solve for t. So I'm at this stage now where I start to solve. So t equals r divided by v naught cosine 25. And now I can plug into number 2. So that'll give me minus h equals tangent 25 degrees. That's the putting that cosine on the bottom there for plugging in for t, and times range. The v naughts cancel out, and that's about it. So then we have minus g over 2, and I put that t squared in there. It's going to be r squared over v naught squared cosine squared 25. So I have a quadratic equation. I'm going to have to solve that quadratic equation in order to get my r, but essentially that's where I'm at. Now it'd be tempting to probably go ahead and solve that by Pythagoreans, or not by Pythagorean, but by just simply the quadratic equation itself. So I'll recast this a little bit. This is going to be g r squared over 2 v naught squared, all numbers we know, cosine squared 25, so all of that stuff are known numbers, times r squared minus r tangent 25 minus h equals 0. So here's the a term of my quadratic equation, the b term, and the c term. So I can now go ahead and use, quadratic formula. So that's going to be r equals minus b plus and minus the square root of b squared minus 4ac all over 2a. Starting up here again after looking at that quadratic, first I'll correct something here. I've got an extra r squared in there. I'm going to have to get rid of that r squared. That's not one I should have in there. So I'll erase that one. That is this guy right there. That's not the r squared that I want. Yeah, it looks like it's not going to let me erase that. We'll do that later. I'll just highlight it. That's not an r squared that we want. It's already accounted for out here. So when I plug it into the quadratic equation, I do get a result. The result is going to be two values. R is 70-80 meters, or R is minus 56 meters. So I think pretty easily we can identify that this R is the right one, 7,800 meters. And finally I was able to go back in there and take care of that extra R squared that was there. So we fixed that. Things that I need for now.